previous lessons, we learned about how to calculate pH or pOH of a strong acid or a strong base. And all we have to do is take the concentration of that base or acid and negative log of it. But that's because strong base and strong acid dissociate 100% of it. Now in this videos, we are going to look at what happens when we have a solution of weak acid and weak base, where they're not going to dissociate 100%, but very small amounts of it. Okay, so in this case, we have a specific name when we have a solution of weak acid or weak base, and the name is buffer solution. And in a buffer solution, which consists of either weak acid or weak base, and in a buffer solution, the pH or the pOH change very little, even when we add strong acid or strong base to that buffer solution. Now, our goal today is to figure out how to solve pH or pOH of a buffer solution. Well, if you look at the back side of your periodic table, and this is the reference for equilibrium, this is what's given to us on the AP chemistry test in terms of what are something that we know about pH and pOH, and how is that related to concentration. So as we go through this problem, I want you to be familiar and use this information given to you and solve the problem, okay? For example, pH plus pOH equal to 14. And what does the letter P represent? If you notice, that little p right there is negative log of something. And of course, the base of this is 10. So let's start the problem. Before we start solving this problem, we need to look at two important terminology. In this case, the Bronsted-Lowry acid. And of course, we're going to abbreviate this with letter A. And the Bronsted-Lowry acid would donate. It would donate a proton, and a proton is basically an H+, okay? And in the process, it will form its conjugate base. And I'm going to abbreviate this Cb. So an acid, one is donated proton, become a base. Where a Bronsted-Lowry base, we're going to abbreviate with this letter B, okay? It would do the opposite. Instead of donate proton, it would accept the proton from the acid. In this case, it would accept a H+. And of course, a base would now become a conjugate acid. So we call this Ca. So if you notice, it exists in terms of a pair. And we have a specific name for this. It's called conjugate pair, either acid-base or a conjugate base-acid pair, because it really exists as a pair. And the only difference between the two compounds in a pair is, of course, one hydrogen plus. And in any solution with acid and base, the acid will neutralize a base in a solution, and a base would neutralize an acid in a solution. What does that mean? Neutralize. That means it will react with that specific substance. So if an acid neutralizes a base, now the base values in that solution will decrease. Okay? As well, the values of the acid will decrease. And if a base neutralizes an acid, that means the number of mole of acid in that solution will also decrease. Because an acid and a base, okay, will always neutralize to form a salt and water. And that's the process of neutralization. So let's look at an example in terms of the conjugate pair. And if you know right here, we have aniline right there. We know there's a 2 right there. I want you to focus on that. Look what happened. Over here on the product side, look what happened. It has a 3. And if we read the problem, aniline, a weak base, that means it's gonna what? Accept a proton. React with water according to the reaction represented above. So in this case, it would accept a proton. Or accepted a proton. And where is the acid in the solution? Of course, it is the water. Notice how water has 2 hydrogen, and all of a sudden we just have 1. So that means water has just donated a hydrogen. So now we have our conjugate pair, okay? So this would be a base versus a conjugate acid. This would be an acid. This would be a conjugate base. We have a pair right there. Isn't that easy? And then for this problem, we're going to write the equilibrium expression Kb for the reaction represented above. And the way it works is pretty easy, okay? When we write an equilibrium expression, we are going to ignore two states of matter. And that two states of matter is liquid or solid. So in this case, we can ignore the water. So in terms of our equilibrium expression Kb, what does the B stand for? This is your base right there, okay? That's basically the product on top and relative to the reactant on the bottom. So we have our product. In this case, again, ignore solid and liquid and write down everything else. So we have a product. And this is relative to our reactant. And notice how I don't have anything to the second power because the coefficients are 1. And that is our expression for Kb. And how is this related to the reference on the periodic table? Of course. Look at this. It's given to the form of Kb. This is there to trick us. But if you notice right there, right? We have our base on the bottom, which is right here. And we have our conjugate on top. So that's one way you can double check your work. Let's look at 1b. So a sample of aniline is dissolved in water to produce 25 milliliter of 0.1 molarity of solution, okay? And the pH of the solution is 8.82. So now we know more about the solution. This solution actually consists of 25 milliliter, and the molarity of the solution is 0.1, and it has a pH of 8.2. Calculate the equilibrium constant, well in this case Kb, for this reaction. So again, Kb, we have our expression, but the expression is in concentration, so keep that in mind. This is in concentration, that's why we use the bracket. Okay, and we don't know the concentration for the OH minus as well as this one right here. But we know the concentration for this. But what's happening here is that we have to realize that this concentration is at equilibrium. When we calculate for our equilibrium expression constant, we are looking at the values at equilibrium. So let's set up our ice table. So based on our ice table, what do we have initially? Of course, we know for sure there is nothing on the product side because we haven't made anything. We haven't let it react yet. And of course, what do we know about aniline initially? Well, we know that the concentration, again, when we write our equilibrium expression, we are focused on the concentration. We know that the initial concentration is 0.1, okay? And what about water? Do we know anything about water? Well, in this case, water is liquid, so we can just ignore the whole entire thing, okay? And what we realize is that when we go changes, we don't know how much change is really happening, so we have to represent in terms of x, okay? And this would be minus x, this would be plus x, and this would be plus x. And at equilibrium, we would apply the two changes. Starting from the initial, we have 0.1 minus x, and here we have 0 plus x is just x, and we just have plus x right there. So this is what we are looking at when we write our expression. So we have our Kb is equal to x times x divided by 0.1 minus x. Now, in most cases, when they ask you to solve for an equilibrium expression values, there is some other information that allows us to solve for the values of x directly. It is hidden somewhere. In this case, if we look at our information over here, right, in terms of what do we notice so far? We need to look for concentration of OH. So let's look for a thing that has OH in it. Well, here OH minus, here we have POH, and here we have pH, which is given to us in the problem, right? So we have pH, we're going to need that somewhere. And we also know that pH is equal to negative log. So in a way, we can relate this together, okay? Basic pH plus POH equal to 14. Because once we find our POH, we can now find the concentration of it. So let me look at this right here. What is our pH? Our pH is 8.82. So what we're going to do is this. We have pH plus POH, okay? You see how we use a reference table to look at our information and find a way to solve it. So this is equal to 14. That means POH is equal to 14 minus 8.82. And this gives us 5.18. Now, again, this has to be converted into concentration. So do we know anything about the relationship? Yes, we know right there. If we look at the concentration, right, we can rewrite this as negative log of OH minus equal to 5.18. This is what we have right there, okay? So P is, again, is just a negative log of this. Now, the tricky part is this log is with a base of 10. There is a logarithm rules that allow us to solve for the concentration. And this logarithm rule look like this. We have b to the power of log with a base of b to the x is equal to x. And this basically cancels each other out, equal to 1. So in this case, if this is our 10, can we just take this to the 10 to the power? But before we do that, we need to bring this negative over here, okay? So we have log of base of 10 equal to negative 5.18. And then we take that 10 to the power of this and 10 to the power of that. Just cancel each other out and give us our concentration equal to OH minus 10 to the power of negative 5.18. 5.18. And of course, we can plug this into a calculator. We have 6.61 to the power of negative 6 right there. But this concentration of OH is not only that it's belonging to OH. If we look at our ice table right here, right? This is our OH equal to X. But what else is also equal to X? What about this right here? So this is also equal to X as well. So therefore, X is equal to the concentration of OH as well as this one. So what we're going to have is 6.61 to the power 2, 6.61, 2. And that divided by 0.1 minus X. And notice how we have 0.1 minus X. Of course, we can substitute that in for X values. But the question is, do we have to? Okay? Because part of the AP test, you have to realize that we have to make sure that the X values is significant changes. Well, one way to do this is look at this problem right here. In order to determine if the values of X is significant or not, we have to compare it to what is it changing from. So in this case, it's changing from 0.1. Now there is a golden rule, is basically 1,000. So if you take this values right here, the original values, and divide by X, if that value is greater than 1,000, that means this values right here must be very small. Okay? And then therefore, we can ignore X. And it turned out, if we do the math behind this, 10 to the power of 4, which is greater than 1,000. So now we can ignore that right there. So for KB, it's just going to be, of course, we can take that to the square. And that turned out to be, or, that's our KB right there. And one thing you need to realize when we work with equilibrium expression, that this values remain the same unless you change the temperature of it. Okay, so keep that in mind. This KB for the whole reaction stays the same, even we add more acid or more base to it. Now let's continue with this problem and we look at what happened when we make changes to this buffer solution. Okay, basically we make a buffer solution. What happened when we add a strong acid to it or a strong base to it? What happened to the pH? So in this case, the solution prepared in part B, which we just did, and that solution is what? It consists of 25 milliliters of that aniline, and the molarity of that aniline is 0.1 molarity, okay, of solution. Now, what if this solution is titrated with 0.1 molarity hydrochloric acid? And this acid, of course, it is a strong acid. That means it's going to be 100% dissociation. And calculate the pH of the solution when 5 milliliter of the acid has been added. So 5 milliliter of hydrochloric acid been added. Well, if you notice, I break down this into parts. And this is basically the part that you require to answer to solve for this pH. But on your AP test, it's not going to give you this part at all. You are expected to solve it directly without any of these hints right there. And one thing you have to look at this is that an acid would neutralize a base. A base would neutralize an acid. In this case, if I'm adding the acid in the solution, of course this acid is going to neutralize the base in the solution, okay? Therefore, the base values in the solution will go down. So we need to look at that values first. How much is it going down? But we cannot look in terms of concentration. It's impossible to do that. We have to look at in terms of the universal unit, which is mole. Every change needs to be calculated in mole when we talk about substance reacting with another substance, okay? So let's write this equation again. So here we have this reaction that we have seen so far. Remember, we're not changing the values of water, which is our acid. In this case, if we're not changing this is not going to affect our problem at all. But what we're going to add in is HCl. But what is HCl producing in terms of an acid? It's producing this H plus right there. So we can cross it out and put H plus there. And how is this H plus is going to be put in this side? Why is it put in this side? Well, this is an acid right there, okay? It's going to react with this base to make more of this conjugate acid right here. That's why I just said before, an acid will neutralize a base to make more of the conjugate. So in this case, what we're going to have here is our ice table again, but this is going to be relative in terms of mole. So keep that in mind. Well, initially, we know that this solution right here is what? It is 25 milliliter at 0.1 molarity, okay? What is that in terms of mole? Well, that's pretty easy. We have to convert the volume to liter first. And then the liter cancel out and give us our mole. Well, we now don't have water, but we have the hydronium ions coming from HCl. What is the initial values? We just add 5 milliliter of 0.1 of hydrochloric acid. So we can solve for, of course, this is coming from 5 milliliter at 0.1 molarity. So in this case, 5 milliliter in terms of liter is, and we multiply that, and this gives us mole. Do we have any of the product produced here at all? No, of course. We haven't let it react yet. So therefore, this is going to be 0. Notice how I also ignore OH minus because we didn't change the water values at all. It's still the same. Now let's look at this ice table. We have our initial values of the base, and this base is going to react with this strong acid. Because this is a strong acid, all this acid will react with this base. So we can see that the change is going to be minus 0.005. And this change is going to do what to this as well? Of course, it's going to neutralize this base, so we would have a minus 0.005 as well. Now you see what I meant by neutralization. So at equilibrium, we take this minus that, give us 0.002. There you go. And over here, we would have 0 because all the acid has been used to react or to neutralize the base. Well, if this is how much being used, and they all have the ratio 1 to 1, therefore this must be 0.0005. So if this is how much is used to react with the base, this is how much of the conjugate acid is going to make on the product side. So on the product side, now we have 0.005 for this conjugate acid right there. But again, we have to realize this is in terms of moles. And we cannot write an equilibrium expression directly using mole. We have to convert to the concentration, which right now our new volume is no longer 25 milliliter, but it's gonna be 30 milliliter And that is coming from 25 plus 5. And the 5 is coming from HCl. And this one is for original in part B. Okay? And we look at our reference again. The pH has to be internal concentration of H plus, OH minus, using the connection between those two. In this case, it's a base, so therefore we had to use this somehow. So how did we figure out the concentration of OH minus? And by looking at this, we had to go back to our equation and see how is this going to change our OH concentration in the reaction. So now we're going to rewrite the reaction again. So this is our reaction that we have originally, right? But now the value has changed because we have the hydrochloric acid added to it. So what's the new value is going to be initially? Now we have 0.002 mole, and let's express that in terms of concentration. So 0.002 divided by 0.03. That's because this is our new volume right here. And what about the water? Well, water, we ignore it because it's in a liquid form, okay? It doesn't change anything. It doesn't evolve in a equilibrium expression. What about this one right here? It's no longer 0 anymore, but by adding that hydrochloric acid, it has given us the initial values, in this case, 0.005 mole. And then, of course, the concentration is going to change as well. What about the initial values for OH minus? This is where it gets really tricky. You have to realize that by adding the hydrochloric acid, it changed the initial values of this. But we had to come back and realize that we still have our reaction where we have the base react with water, but nothing happened yet, okay? It's like a reset to some extent. So, of course, we have 0. So it's like the same assumption we make before where we have the ice table right here, where we make an assumption is actually 0 with the initial concentration of 0.1. But now we're adding the hydrochloric acid. This initial has changed, and this initial has changed. So it's like a reset, but not really a reset, okay? So keep that in mind. That's the tricky part. Now let's calculate and express in terms of our concentration. We do the math, plug into the calculator, and this gives us 6.67 times 10 to the power of negative 2. And this gives us 1.67 times 10 to the power of negative 2 as well. What about the changes? Of course, this is going to be changed in terms of a certain values that we don't know. So we're going to represent this by x. But is this x is the same thing as the x values here? No, because we have added in a strong acid, and that would change the whole entire thing. So this is a variable. X is a variable, okay? So the best way is probably to call this y or something. Minus y. How about that? Let's do that. Minus y. Because this is the new one, okay? And of course we ignore the water, and this would be plus y, and this would be plus y as well, okay? So that way we don't get confused that this x is the other x. No, it's two different variables because they are in two different conditions. So our change is in this case 6.67 e to the negative 2 minus y. And here we have 1.67 e to the negative 2 plus y. And this just gonna be y. And y is representing the concentration of OH minus. Okay? So keep that in mind. Now we have everything expressed in terms of concentration, so we can solve for this directly. Solve for this right here. Because we have our Kb, which is an equilibrium expression for this reaction, and equilibrium expression doesn't change until we change the temperature. In this case, the temperature stays the same. So we have our Kb, which is 4.4 times 10 to the negative 10, equal to the product of this, 1.67 e to the negative 2 plus y times y divided by 6.67 times 10 to the negative 2 minus y. Okay, there you go. And if we keep the plus y and minus y, the math would be super complicated for us to solve, okay? And one beautiful thing about the AP test is that it is safe to assume that the values of y is very small, so we can neglect it or we can ignore it. But there is a golden rule that we can use to actually prove that we can ignore it, proving that the y values is small. And all you have to do is take your Kb or your Ka, time that by 100, in this case Kb, and we are going to compare to our initial in this case 1.67 times 10 to the negative second for that one, or 6.67 times 10 to the negative second for that one. So it doesn't really matter, let's choose one. They're both to the 10 to the negative second. And we do that, 6.67, let's use that one. Well, what is our KB in this case? It's 4.4. So we take 100 times that, right? Which is turned out to be still a very small number to comparing to our initial concentration. And let me do the math for you, so that way you know what's it gonna look like. So we take this time of KB, 100 times 4.4 e to the negative 10, and that turned out to be 4.4 times 10 to the negative 8, which is a lot smaller than 6.67 e to the negative second. So now we can ignore this. There you go. And with this information, now we can solve for the y variable, which is, y is going to be equal to, using your basic algebra skill. And I'm going to set this up for you. Of course, we're going to multiply this over here, and we're going to divide by that. And a y turned out, which is, a y is a concentration OH minus, equal to, see, a y is a concentration OH minus. It's going to equal to 1.76 times 10 to the negative 9. And this is a concentration OH minus as well. And of course, if we have the concentration of OH minus, now we can take that and find our POH. And P again is the negative log of OH minus, which in this case is that values right there, okay? So let me rewrite it again for you. Negative log of 1.76, negative 9, and that equal to 8.76, and that equal to your POH. And how do we calculate our pH? If we have our POH, we'll go back to our reference again. pH plus POH equal to 14. So now we would have pH equal to 14 minus 8.76, and our pH is equal to 5.24. But before we end this problem, let's go back and look at our reference to see if we can find another way to solve this problem a lot easier. You see right there, this equation right here, that equation is a special equation called the Handerson-Hasselbalch equation. And if we look at the Handerson-Hasselbalch equation, it's allowed to solve for pH. If this allows us to solve for pH, can we just solve for POH? Well, we can actually rewrite this equation in terms of POH the same way. So of course, we have POH, okay? But we're not going to use Ka, we're going to use PKB. Isn't that easy so far? What about this part right here? Plus log. Notice how this is your acid right there, right? And what is this? This is the conjugate base. Can we do the same thing to the base? Of course, we're not going to have an acid on the bottom. We're going to have a base on the bottom. And on top here, we would have a conjugate acid concentration. Isn't that easy? In terms of taking that Handerson-Hasselbalch equation in terms of pH and solve it in terms of POH. Very easy, right? Well, let's see how the math has become a lot easier. I'm going to rewrite this over here, okay? So we have P. What does P stand for? We have negative log of our KB, which is, we know that's 4.4 times 10 to the negative 10. That's easy so far. What about our concentration? What about our concentration of the base and the conjugate acid? Well, look at what happened when we adding in the hydrochloric acid, right? What happened to it? Well, let's look at our buffer solution. What happened when we add in a strong acid and we have this new concentration for the base and the conjugate acid? Well, we just solved that right there. That is your base concentration, and this is your conjugate acid concentration. So all we have to do is plug that in, which we know is 6.67 times 10 to the negative 2. And on top of here is going to be 1.67 times 10 to the negative 2 as well. And all we have to do is plug it into the calculator. And look what happened. Our pOH is equal to 8.74, which is what? Which is very darn close to what we just saw before. Where is it? Right there. We have 8.76. That is super close, okay? So we can now actually accept that values. And to solve for our pH, we just take 14 minus this right here, 8.74. And this gives us 5.26. And this is very close to that. And so learn how to use your references on the backside of your periodic table, especially the Handerson-Hasselbalch equation when it comes to the pH of buffer or the pH of a buffer. It makes our life a lot easier, isn't it?